despite all those places that I've been and where we met, I was actually born 8 miles from here. So this is like a coming home for me. Also, I just wanted to point out that it's okay to interrupt me in the middle. I'd rather sort of address any questions or things while I'm talking about it than wait till the end, or also take questions at the end too, but feel free to interrupt. So I'm going to be talking about making nonlinear measurements in the Earth. And so I'm going to start with some definitions and why we should be doing this and stuff like that. So what I'm going to be talking about, this is really kind of the core motivation in the middle. And what this is an experiment taking a piece of rock in a laboratory and then progressively damaging it from 0 to 1. It's just kind of a normalized measurement of going from intact to failure. And these are just some measurements that we can make on that object. And over here, P, that's essentially the P wave velocity, that's the linear elasticity, changes by some small amount. So you can imagine if something's damaged, it tends to get slower because you have all these sort of internal contacts that are compliant, makes the material softer. We can also measure Q or attenuation sometimes because that's more sensitive to some of the things that we care about. But up here is this alpha term, which I'll describe later, which is related to the nonlinear elasticity of the material. This is on a log scale, so we can see how much these parameters change with essentially the damage of a material or the amount of sort of internal compliant contacts. And so if we want to be measuring things like fractures and faulting in fluids and things like that, nonlinearity is much more sensitive to these kinds of things than a linear elastic measurement. And so that's why we want to be making these in situations where we care about things that are stress and strain sensitive, like porosity, permeability, how intact a material is, all that kind of stuff. So the way that we measure that in the lab is with this idea of called pump and probe. The pump is sort of a low frequency straining of a material. And then the probe is measuring how its elasticity changes by like a travel time or something like that. So you can imagine getting a time series of an elastic wave speed at different strain values. And so that gives you this measurement of M as the modulus as a function of strain, or the strain derivative of modulus. And so those are the kinds of measurements that are going to be really sensitive to these internal compliant contacts within materials. Now, of course, we know that rocks are very heterogeneous materials with grains, fractures, faults at all scales, from sort of microscopic to things that you can see with your eye.
Can I ask a question?
Yep.
Sorry, I came in late, so you may have said this, but why are you looking at the radiation modulus with strain as opposed to with stress?
Well, I mean, it's strain is something that, I guess, one thing you can measure strain a lot easier than you can measure stress, and they're related to each other just through the modulus. So essentially, it doesn't matter too much. I mean, the modulus is both stress and strain sensitive.
Right. And so it's because strain is easier to measure than stress.
Yeah, exactly. Yeah.
I didn't know if there was something fundamental about it.
Not really, but that's typically what's done in the laboratory and the way I'm going to talk about it in the Earth. Okay. So I'm going to go over some definitions first. So we have classical nonlinearity. So that's essentially Hooke's law with higher order terms. So F equals kx, or sigma is mod in terms of a tensor, looks like that. So that's related to the anharmonic properties of materials, not compliant internal discontinuities. So that occurs in single crystals and other intact or homogeneous materials. So if you take any kind of even something that's fairly homogeneous, like say a metal bar, and you heat it up, for example, it would have different properties. Those are kinds of anharmonic properties. Then we have hysteretic nonlinearity, so elastic behavior with memory. So this has time-dependent processes built into it. So you could think about something that almost like what we were talking about this morning, where you have stress applied to a system, and then you have granular material that reacts over time to that stress or something like that. So that's related to the contact properties across compliant material discontinuities. So you have internal contacts that have time-dependent properties in terms of their stiffening and softening. So this only occurs in damaged, granular, or other heterogeneous materials. And then we have different kinds of responses of a system. There's fast dynamics, which is the instantaneous dynamical response of a system. And it's related to putting a material into disequilibria or a new equilibrium state. So you can imagine if you compress a material, it'll get instantaneous faster if you're sort of closing up compliant internal contacts, but also there'll be the slow dynamical part of it, which is a time-dependent process, and that's related to a material disequilibria in the process of reacquiring some kind of equilibrium, either the original state or a new state. So these are concepts that are primarily derived from physical laws and laboratory experiments. So why should we be studying this in the Earth? Well, faults, fractures, pores, grain boundaries are the source of nonlinear elasticity. These are just some examples of what rocks look like if you put them under a microscope. And as you can see, they have crystal grains that are, micron scale or, tens, hundreds of microns, kind of like that. And so you can imagine that the way that stress is transmitted across something like this is pretty heterogeneous. It would go, the elasticity of the grains themselves matter, but also the contact properties and how stress is transmitted across those boundaries. So when we want to monitor systems regarding hazard, porosity, permeability, and solid fluid interactions, those things are all occurring essentially at these compliant boundaries. So we also care about stress and material failure. The integrity of a material has a lot to do with what these contacts are doing. And the macroscopic elasticity of materials is determined by grain properties, contact properties, force change, geometry, all that kind of stuff. And we can also leverage the substantial laboratory and theoretical work on rocks to try to understand what we can observe in the Earth. But a main challenge is that making the same kind of measurements in the Earth that are done in the laboratory. In the laboratory, you can have a rock on your table and you can apply various stresses or pore pressures and all kinds of things like that. And then you can measure it, but that's kind of a harder thing to do in the Earth. So why are rocks nonlinear? I've sort of talked about this already, but the effective elastic modulus is something you'd measure just with a seismic travel time. It's dependent upon all these things: the grain coordination number, that's essentially the geometry of the grains and how they come in contact with each other, the contact stiffness, the contact geometry, which are all affected by the stress state, porosity, pore fluid, and elastic properties of the grains. And so those are the things we often care about: stress, porosity, pore fluids. Those are the things that are primarily occur at these internal contacts. So you can imagine that for each possible grain configuration, there'd be a different stress state. If you reoriented these or you disturbed it in some ways, then the way that stress is transmitted across this rock will change, even though the grains themselves aren't really any different than they were before. They have the same linear elasticity that they had before, but the contacts could be different, and the way stress is transmitted through that rock could be different. So of course, this happens at all scales. This is just sort of an example of what a fault zone might look like. We have a damage zone that could be anywhere from centimeters, meters, tens of meters, depending upon how mature the fault is. And then you get this sort of gradation of damage as you go away from the fault. This is just sort of a map scale. So you can imagine some areas where this zone is very narrow and other areas where it could be kilometers across. So we can study the nonlinear behavior of fault zones to get an understanding of stress and frictional evolution, things like that. So this is just a diagram of what it may look like sort of in a mathematically. So in these plots, we have strain is on the horizontal axis and stress is on the vertical axis. And so the slope is the modulus. And so this would be a linear system. So essentially the stress and strain are just linearly related, go up and down like this. And this would be what the traveling wave would look like. And then you can have classical nonlinearity, which is just the same function, but with some higher order terms. So it's there's still no memory to the system, but it's not a linear relationship anymore. And then we have nonlinear hysteretic behavior, where you have this kind of a system where it's dependent both on the strain, but also on the path. So it has memory to it. So at any given strain level, you can have more than one modulus depending upon what the history of the stress strain function is. And so this alpha parameter, which I talked about before, is what's related to the hysteretic behavior. Okay, so I just want to give an example starting out how do we observe these things, because sometimes when you see a parameter in an equation, you kind of understand what it's doing, but it's hard to know how it would be measured. So this is just an experiment that took place at Penn State, and this is just two samples of rock over here, and there's they're measuring permeability. And then they have a shear load and a normal load, and they're measuring the travel time across it like this. And as it relates to a cyclical strain applied to it, as well as a cyclical pore pressure. And what you can see, so up here, this is a cyclical pore pressure in blue, a cyclical strain in black, and this is the thickness. So you can see with the applied normal strain, there's a normal stress. There's a change in the thickness, not for the pore pressure. And right here, this is that travel time of that wave that's going across the system. You can see that it reacts to either the applied normal stress or the applied pore pressure. And what you can see is it goes up and down like this, but there's also a step change. So you can see it goes from faster to slower. And so the drop between here and here is related to alpha. So you have both a strain and a strain right there affecting the elasticity. And so that's that part of it that's sort of history dependent, that's rate dependent. And then this sort of high frequency correlation here between the applied stress and the travel time, that's the beta term, or the sort of the classical nonlinearity. So that's the Hooke's law with an extra term in there, and the step drop is that alpha term. And what you can see is that there's both fast and slow dynamics. So there's an instantaneous response to these two perturbations, but there's also this delayed response where first you have a drop and then over time it recovers. And that's also related to the permeability, which is down here in the blue. The permeability increases and then it decays over time. So this is just a sort of a laboratory example of of the relationship between those equations and what we actually see in an experiment. So some other applications are how can we know where we are in a slip cycle? So this is just sort of an example of the earthquake cycle. We have the interseismic period where the slip rate is slow, nucleation where the slip is increasing, post-seismic, which is the actual earthquake, and then post-seismic where the slip rate is decreasing. And one question is, how does the nonlinearity change in this cycle? And so how do fluids affect the contact properties and force chains? Can we know fluid and poroelastic conditions by measuring contact properties, nonlinear behavior? So these are two sort of important applications. Can we know anything about stress, strain, and the integrity of a fault? And can we know anything about pore fluid pressure and permeability and sort of rock fluid interactions? And so I'm going to talk about these a little bit later. So I'm going to show you some examples at Earth scale. These are previous studies that sort of motivated a lot of this work. So if we're going to act in the earth, then we need some kind of a natural pump. In the laboratory, we just have some kind of a mechanical system that can apply a strain to a system. The two effects that are the largest in the subsurface are the barometric pressure. So the barometric pressure imparts strain in the earth, and that can be measured in terms of oftentimes in pore pressures and things like that in the subsurface. And the other one is the solid earth tides. The solid earth tides is the gravitational pull of the moon and the sun on the earth as the relative locations of the heavenly bodies affect each other. So in particular, the biggest effect is that the earth is rotating relative to where the moon is. And so when you're facing the moon or facing away from the moon, the strain field is different than if you're perpendicular. And so that's the dominant cycle that you would see if you were measuring the strain in the earth with a strain meter or something like that. And so we also need a probe. And for the most part, I'm using differential Green's functions as the probe, and I'll talk a little bit more about that later. So this is something that I think is a really interesting study. So this is getting back to, can we see where we are in the earthquake cycle by looking at nonlinear behavior? And so this is similar to something we saw earlier today. This is the coefficient of friction, or the shear stress over the normal stress. This is sort of a rate and state friction formulation here. And so we have a nucleation where you have dilation and a reduced modulus during the nucleation because of the as a fault is going to fail, it essentially needs more space to slip. So there's always a dilation in the granular material during slip, or as slip is nucleating. So there was a study in Parkfield, and what they did was there's the SAFOD hole, which the goal of it was really to drill right into the fault zone. But they also have this pilot hole right next to it. And in this experiment, they had a source and a receiver. So essentially beaming an elastic wave from one hole to the other, and measuring the travel time and how that evolves over time. And so this gives us this sort of time-dependent behavior. And the interesting thing was, it was the biggest effect was barometric pressure. So they could measure how barometric pressure changed the travel times due to the stresses and strains in the earth. But this is a time series over here. I'm going to get your attention down here on the bottom right, and this is the delay time as a function of time. So this is over about let's see, this is days right here. So 5260. This is about a week or so, and they recorded it during a couple of small earthquakes. So this is where the wells are right here, and then there was this earthquake here in red that was about a magnitude 3, I think, and then this other one which is about a magnitude 1, and they are measuring just the travel time between those two wells. And what you can see here is that the travel time increased at the time of the magnitude 3 and also at the magnitude 1, but the important thing is actually started to increase like a day before the earthquake actually happened. And so essentially this forecasted an earthquake the day before it happened. And that's also true of the magnitude 1, but it was only a few hours. And so this is the kind of thing that we can see with the nonlinear elasticity that you can't see with traditional seismology. And these are the kinds of things that we can measure. Essentially, we're measuring the dilation associated with the nucleation of an earthquake. And so this is some kind of slow dynamics where the system is evolving over time. Okay, I'm going to talk about another example now. So this is again using this one is using the solid earth tides as the pump. And what I'm showing you here is there's a shear and a normal component to the solid earth tides. The blue is the normal part, the red is the shear part. And then using a natural probe in this case. So I'll show you what this looks like. So using empirical Green's functions, this was in California at Pinyon Flats. and they had a seismic array, and they're just measuring changes in the empirical Green's functions in the coda part of it. So this is a scattered wave field that samples sort of a region within the array. And what they're doing is they're breaking up the tidal cycle into parts when the Earth is in compression versus extension. And so they're measuring small phase shifts during different parts of the tidal cycle. And so this is just them breaking up the tidal cycle into different components and then measuring the empirical Green's functions and looking at how the velocity changes. And what they actually measured here was that the Earth actually gets slower when it's compressed and faster when it's extended, which is sort of the opposite of what you might expect, because normally we think if something's all fractured and you compress it, the internal compliant surfaces will get stiffer. But in this case, they're measuring very shallow structures, so the upper few meters to tens of meters, and it's there's fluids involved, and so actually when it gets compressed, the pore pressures go up and actually has an opposite effect on velocity. So this is like a dilatant material, and it's the same thing as like when you step on the beach on the wet part of the sand and the water around you seems to dry out. I don't know if anybody's ever noticed that, but it's not because you're squeezing the water out or something like that. It's actually the opposite. You're actually, by compressing the sand, you're actually opening up the pores, and then the water gets sucked in there, and that's why it looks dry. So you're not actually squeezing the water out, you're actually drawing the water in under your foot. So, but that's what they observed in California. And so now I'm going to talk about another study with an artificial probe. So that was a natural probe, and now we're going to look at an artificial probe. This is, I think, one of the most exciting or interesting studies that have been done in the Earth. This was in Japan, and they were in a cave right by the shoreline, and they had a source and a receiver at two different branches of the cave. So I just kind of drew this just as a schematic because the figure in the paper was hard to reproduce, but and they're just measuring over an entire year the travel time between these 2 points going through the rock. And this is what it looked like, a representative. This is about a 14-day period. So what we're looking at here is the strain. So they had a strain meter there. And so this is EXY. This one right here is the aerial strain. This is the sea level. So this is related not to the solid Earth tides, but actually the ocean tides, because they were sitting right next to the ocean. And so this is with the ocean level going up and down.
What do you mean aerial strain?
So the horizontal 2D tensor.
Oh.
Yeah. And so what you can see here, this is the strain. And I just kind of drew this on here to say that it's not completely symmetric, but the amplitudes are bigger in the middle. And this is the time when the tides are the highest, and at the edges when the tides are the lowest. But if you look at this one, which is the differential travel times, the peak to peak amplitude doesn't change very much over the cycle, even though the strain does. And so this is asymmetric relative to this, but you can also kind of see that the mean changes. So if you were to take a running mean over here, it wouldn't change very much. But if you take a running mean here, it does change. So this is an indication of slow dynamics as some kind of time-dependent process, whereas this isn't behaving. If it was just a linear relationship, you would see this being just some kind of multiple of that, but it doesn't look like that. And so this is what it looks like in terms of the differential travel time, which is here. That's kind of the peak to the trough. And then this is the aerial strain. And so what you can see as on the right-hand side, which is when it's extended, there's something that looks like a linear relationship between the travel time as a proxy of the modulus and the strain. So that means as it extends, it gets softer, the travel time goes up, and it looks like a roughly linear relationship between the two. But when you go to on the compression side of it, the amount of reduction in the differential travel time doesn't seem to be sensitive at all to the level of strain. And so there's this asymmetry here where there's a strong dependence on the strain magnitude when you're in dilation, but not when you're in compression.
And I'm a bit curious about the travel time difference, the order of the difference as 10 to minus 7.
Yeah, 10 to the minus 7, yeah.
This is absolute travel time difference.
Yes,
That's-
yeah, very small.
Yeah, and you are able to measure it?
Well, in this study, they had an active source, and so they knew what the source was and exactly when it was transmitted. So it was sort of a controlled experiment. I mean, they had, since it's an artificial source, they knew exactly everything about it that they needed to know. Okay, so this is sort of a really interesting observation. It's an asymmetry between the dilation part of it and the compression part of it. And so they sort of presented this in a different way. This is the travel time at the peak strain and the peak strain amplitude. This is a roughly sort of linear relationship here. But then there's the travel time peak to peak amplitude versus the strain peak to peak amplitude. And there's a saturation. So as we saw a couple of slides up, the amplitude of the strain changes quite a bit from in the middle here when tides are high versus low, but the peak to peak amplitude there doesn't change much at all. So that's that saturation where the peak to peak amplitude never gets bigger than some amount. So there's maybe some fast dynamical part of it that it does react right away. But then there's this other part that doesn't seem to really react at all because whatever the response is slower than the applied strain or something like that. And so they talked about it as this rate dependence where the crack closure rate gets smaller as the strain rate increases. That's I mean, that's a perfectly correct way to say it, but I interpret this as the crack closure rate is not dependent on the strain rate, but rather something else. So when you're on the compression side of it, it doesn't seem to depend on the strain or the strain rate. It just has to do with something else. And so what I did is I decorated this a little bit more. I looked at two different strain levels at the high end of it and at the lower end. So these top three are all, well, these top two are the same figure as this. It's just that I drew a red line across when the strain is extensional and a blue line when the strain is compressional. And I just marked on here what the differential travel time was at each of these points that are at the same strain level. And then I kind of slid it down here so we can see it, and then I vertically exaggerated so we can see it a little bit better. What you can see is there's this behavior where it's slower or softer when the peak to peak amplitude is bigger. There's some points over here that I'm not quite sure how to explain, but in both when you're in the compression side of it and the extension side of it, it's softer when the amplitude is bigger than when the amplitude is smaller. So that's also an indication of this sort of slow dynamics, that it's not an instantaneous response. Otherwise, this would just be kind of flat across like that. So just to summarize, the travel times are shorter when the rocks are compressed than when they're extended. That's true everywhere. The rock is softer when the peak to peak amplitude of the strain is higher. This indicates slow dynamics. And the process of softening is at least as fast as the 12-hour dominant period of the strain cycle. So when it gets softer, it's an instantaneous response. It doesn't, so it's whatever it is, it's faster than the actual rate of change of the strain. But the process of stiffening is slower because it never catches up. It never gets sort of as stiff as you might expect it to, over that 12-hour cycle. Okay, so my interpretation is that the relaxation rate during extension is fast. The relaxation rate during contraction is slow. The period of the strain oscillation is constant, and the peak to peak amplitude and travel time is nearly constant. So the peak to peak amplitude and travel time is primarily determined by relaxation rate, not the strain amplitude. So then I was thinking, so how would this behavior work in an anisotropic stress field like that in the Earth's crust? So in this experiment, there was no, at least they didn't measure the anisotropy, but they were just measuring one azimuth, so they wouldn't have detected any differences anyways. But if there was an anisotropic stress field, how would that affect this behavior? So if we think about the deviatoric part of the tectonic stress, it's on a megapascal scale. We don't necessarily always know what the magnitude is. We often know the orientation, but it's probably a few megapascals, maybe tens of megapascals. It's almost always anisotropic in the Earth. So I always have a direction of maximum horizontal compression, usually denoted as SH max, and then SH min would be the opposite of that. And it's constant over the sort of time scales that we're talking about here. The tidal stress is only kilopascal scale, so it's about 3 orders of magnitude less. It's greater along an axis pointing at the place on the Earth closest to the moon or the sun. There's a little bit of a lag to that, but that's more or less true. There's about a factor of 2 at the mid latitude that's latitude dependent, and it alternates between compression and extension. So this is a cycle that has many different components to it, but the dominant one is about 12 hours or so. And so it goes alternating from compression to extension in all directions at the same time, roughly the same time. So if you can imagine different fractures, or think about compliant internal structures and different orientations, right here I'm showing an example SH max here. And if we think about fractures that are oriented this way, so it's kind of in this, that open up perpendicular to SH max, then SH max will always be trying to keep them open in a sense. So trying to close up fractures going this way and open them up this way. And if you have it the opposite direction, then you have SH max trying to close these fractures. And so fractures in different orientations will have a different relationship with the tectonic stress field. And so what I'm going to try to describe here is that the response to the tidal compression will be faster here because SH max is pushing in the same direction, and slower here because SH max is pushing in the opposite direction. So then we have this stress-induced anisotropy. So the peak-to-peak amplitude and travel time is primarily determined by the relaxation rate, not the strain amplitude. So we saw in that other experiment that the amplitude doesn't actually, the amplitude, and we're talking about the tidal stress now, the relaxation rate due to the tidal stress is not dependent upon the amplitude, but it's related to the relaxation rate. And so when we measure the changes in peak-to-peak amplitude and the travel time, we are really measuring changes in the relaxation rate. And so this would be fast, and this would be slow. So in the Earth, we can use this pump probe, but we're going to use, in this case, we're going to use, we're going to use the differential Green's functions again, and we're going to use the solid Earth tide. So the tidal forcing would be this part of it. So it's a slow, sort of low frequency pump. And then we're measuring the travel time, or in this case, differential travel times with empirical Green's functions. And so we can divide time up into periods of time when the Earth is in extension, which is up here, and compression here. So this is the tidal strain, and this is just over time. So each of these, big cycles here is about 14.7 days. That's half of a month or half of a lunar orbit. And so then what we can do is compare the velocities when the Earth is extended to when the Earth is compressed, and see what the velocities look like. And if we measure that as a function of azimuth, so we can have 2 stations, and we're measuring the travel time between those 2 stations, and we can measure at all different azimuths, then we can measure this stress-induced anisotropy. And so I've done this in a couple different places. This is in Oklahoma. So this is over here is just an array of stations, which are the red dots. And I do different subarrays. The filled in circles are the ones that I'm using for each of these calculations. And what I want to do is measure the variation due to the relaxation rates, which is due to the anisotropic stress field. And so the minimum here is the area where that peak to peak amplitude is the biggest in the velocities, and that will be the orientation of SH max, because that's the direction that the tectonic stress field is speeding up the relaxation time. And then over here, where it's slower, or a smaller negative magnitude because of the sign convention I'm using, is where the relaxation rate is slower. And so we can see, if we compare the minimum in this curve to other measurements of the orientation of SH max, which are these black lines here, the estimates that I get are within a few degrees of what's measured in, these are, some of them are borehole measurements, and some of them are earthquake focal mechanism inversions. And so these are all things that came from the world stress map. And so this is essentially a stress probe for, by looking at the stress-induced anisotropy in the Earth. We're also doing this in Europe, and this is Janke Eyman, who is a student in the University of Vienna, and he's applying this in the Alpine foreland. So this is Central Europe. Up here is Germany, down here is Austria, in Italy, and Switzerland. And these black lines here are measurements of SH max orientations. And most of these are from boreholes, I believe. And these are seismic stations in red and blue. And so he's using these seismic stations to measure the azimuthal dependence of this nonlinear behavior to try to fill in some of the gaps, in areas where we don't really have any other kinds of measurements. And so those are some of his results so far. The red lines here are the estimates from the stress-induced anisotropy, and you can see they match quite well in areas where they coexist, and also fill in areas where there are no other measurements. And then he's drilling down and looking at some more specific regions both within the Alps and also north. And so the benefit of this is that it really can be applied anywhere you have a seismic array. A lot of these other station measurements are either from boreholes, which there aren't very many of them because they cost a lot of money to drill, and also earthquake focal mechanisms. You can only do those kinds of inversions in places where you have lots of well-recorded earthquakes. So if you could just throw out a seismic array and you can make these kinds of measurements, it can be applied much more widely than the way we do it now. So I'm going to move on to another kind of an application. So I said earlier that it's related to the material integrity. So not only is there this stress-induced anisotropy, but we can imagine that material that is weaker or more damaged will have different behavior than something that's more intact. And so we can explore this in a fault zone to see if we can measure the differences in properties of rocks across the fault. So just to kind of refresh your memory a little bit from what I showed you before, we often use linear elastic measurements to infer material damage or other properties related to damage, such as permeability and pore pressure. However, nonlinear elastic parameters are much more sensitive to material damage than attenuation or linear elasticity. So this is an equation I showed you before, but the linear part of it is this first part, and then this beta is the classical nonlinear hysteretic, classical nonlinear parameters, just the second order term. And then we have this alpha, which is the part of it that's dependent upon both the strain and the strain rate. So this is the hysteretic part of it. So we can imagine that if both beta and alpha were 0, then this is what it would look like. The modulus now is on the vertical axis, and the strain is on the horizontal axis. So essentially the modulus never changes, no matter how much the strain is. In the case where a beta is 0, but alpha is not, you get this kind of behavior where you get hysteretic behavior, where it's path dependent, there's memory to the system. And then if you have just beta as non-zero, then you get something that looks like this. And if you have both of them non-zero, then it will look like this. And so this tells us a little bit about the different parameters. And that sort of relates to this figure I told you up here, where we'd like to be able to measure alpha, because that tells us a lot more about what's going on with the material integrity than the P-wave velocity or attenuation. So we're doing the same thing. We're measuring the coda part of the empirical Green's function, small phase shifts, the differential travel times. And we're looking, in this case, we're actually looking at many more things. So I'm looking at extension, neutral, and compression. But then I also look at the strain rate. So essentially I take this function, take the derivative of it, and then the time derivative, and then I look at when the strain is increasing, decreasing, or neutral. So there's sort of six measurement points, and I try to reconstruct something that looks like this. Try to reconstruct the modulus versus strain cycle. So select negative, neutral, and positive strain and strain rate. We use separate empirical Green's functions for each of these 6 bins. And then we measure travel time differences for 5-second waves between the different empirical Green's functions to constrain the nonlinear elastic behavior. So I also look at different paths. So this is each of these vertices is a station, and so these are just the paths between the stations. So I broke it up into 4 different bins. There's the exterior paths, which is the paths that are the furthest away from the fault. We have crossing paths, and then all paths, and then interior paths. So interior paths are just the ones that were sort of closest and most parallel to the fault. And we can compare these and look at the different kinds of behavior for each of these groups of station pairs. And so what I'm showing you here are the results. The stars represent the measurement points. So this is for exterior paths, all paths, crossing paths, interior paths. And then what I've drawn in the middle is just my possible interpretation. Since I can't measure it with the same kind of time resolution that you can in the laboratory, I can just measure certain points. Then I have to kind of interpolate in a sense. Now, these measurements here are for the strain magnitudes, and these measurements down here are the strain rates. The magnitude of the strain rate has to do with the area within the loop. So if these were 0, then the area in the loop would be 0, it would just be a line. And if it's positive, then it rotates one direction around the loop. And if it's negative, it rotates the other way around the loop. So those are just the things I have to constrain these hysteretic loops. So again, these are possible interpretations because I have just a couple of points on each one. Plus I have some information about how much area should be within that loop and which way it travels. And so we can think about this in terms of the nonlinear elastic equation. So we detect increasing material damage with decreasing distance to the fault because we go from here to here, and in the slope, which is essentially beta, it gets bigger. But alpha is a little bit harder to interpret because the magnitude is smaller as you get closer to the fault, but it's opposite sign as well. And so I tried to look for examples in the laboratory to try to interpret this, but these are the observations. We know that beta and alpha must be non-zero because if they're both zeros, I showed before, we just have a horizontal line. And ultimately, the goal is to improve the time resolution so that we can literally trace, at each cycle, but that's hard to do in the Earth right now. So as I said, I looked at some other examples in the laboratory. This was a paper in 2015. And the reason why I ended up plotting in this way with the modulus on the vertical axis and strain on the horizontal axis, because that's how all the laboratory people do it. And that way we can compare them directly. And so these are just different kinds of rock. And these are the different behaviors. And so we can see that, obviously the behavior is more complex than I can interpret with my results, but they look fairly similar in the sense that, of course, it gets softer when it gets extended and faster when it's compressed. And as far as the direction of the loop, we can also compare those two. And so it looks, they look quite similar. And these are, of course, intact samples, and these are laboratory, small pieces. And so, but at least we can confirm that the behavior in the Earth is pretty similar to what we see in the laboratory. There's also this other neat experiment where they used a vibra-sized truck and an array of instruments underneath it. So the pump is now this truck, and then the probe was just some measurements that they were making in the subsurface. And this is a shallow in situ. And so this right here is the figure that's comparable to what I have over here. So we can see here that the direction is counterclockwise, which is kind of similar to these, like right here. So the shallow subsurface in this experiment looks kind of like our, not the internal paths, but these over here, either the crossing paths or the all paths, which is kind of an average of the whole area. So our results are pretty similar to what they see here in this Vibroseis experiment. And so that's it. So what I wanted to just put down a few things that I wanted to summarize. The rocks are nonlinear elastic materials. It's mostly due to internal context, such as grain boundaries and fractures. Most of the properties that we care about in geophysics happen in internal context. That's maybe my bias, but at least in the shallow subsurface, these are the things that really drive a lot of the things that we want to be able to measure and observe, and that we can probe the behavior in internal context by measuring this nonlinear elastic behavior.